I want you to imagine, just for a second, right? A completely normal morning.
Okay, setting the scene.
Yeah. You're in your kitchen, the coffee maker's bubbling, you're just casually scrolling through your phone, catching up on the news, maybe checking the weather.
Right, very standard.
Exactly. The sun is shining. It is the absolute definition of an ordinary day. And then, abruptly, every screen in your house, your phone, your TV, your tablet, they all just suddenly flash to a global emergency broadcast.
Oh, wow.
And the message is simple, but it's basically entirely impossible to comprehend. It says a black hole has appeared in our solar system.
Just out of nowhere.
Right out of nowhere.
Right.
It is just zero point 0.1 light years away from Earth, and humanity has exactly 24 hours before its gravitational effects reach us.
I mean, that is just the ultimate nightmare scenario right there.
It really is.
And what makes it so chilling is that the sequence of events isn't, it's not magic. Once an object of that mass is in place, the clock that starts ticking is governed by absolute merciless physics.
Right, and we are going to explore that ticking clock today in this deep dive. We're using this really brilliant, deeply unsettling thought experiment put together by the Dark Matter Files on YouTube.
Yeah, it's a fascinating script.
It is. We're using it to map out the scientifically accurate timeline of what would actually happen if this impossible scenario took place. And for you listening right now, while this sounds like pure science fiction, we are going to use this timeline as a shortcut to understand some very real, very intense physics.
Exactly. No heavy jargon today.
Right, no jargon. We're talking orbital mechanics, extreme gravity, and ultimately human nature.
Because the way a planet dies from a black hole is, well, it's a process. It is a sequence of escalating systemic failures.
Escalating failures, yes.
Right, and looking at it chronologically really reveals just how fragile our existence in the solar system really is.
Okay, let's unpack this, because before we get to the actual destruction of Earth, we need to understand what exactly has shown up in our cosmic backyard, because not all black holes are created equal.
Oh, far from it. You have a massive range. At one end, you have supermassive black holes.
The really big ones.
The absolute titans, yeah.
Yeah.
The ones sitting at the center of galaxies, including our own Milky Way. We are talking millions or even billions of times the mass of our sun.
Wow.
Yeah. And if one of those showed up, the 24-hour timeline wouldn't even exist. We'd be gone in a blink. Their gravitational reach is simply too vast.
Right. And then there is a middle ground that scientists are actually still trying to figure out.
Right. Intermediate black holes, yes. These range from 100 to maybe 100,000 solar masses. They are sort of the missing evolutionary link in astrophysics.
Because we don't see them very often.
Exactly. We find very few of them, which makes them incredibly mysterious. But neither the supermassive nor the intermediate is our villain today.
Right. The antagonist of our specific story is the third kind, a stellar black hole. Specifically, one that is roughly 10 times the mass of our sun.
Yeah. And a stellar black hole is essentially the corpse of a massive dead star that collapsed in on itself.
Just crushed under its own weight.
Exactly. And 10 solar masses is relatively modest in the grand scheme of the universe, but locally, in our solar system.
It's huge.
It's a gravitational wrecking ball. It is more than enough to completely dismantle our solar system.
The most terrifying part of this whole thought experiment to me is the stealth factor.
Oh, absolutely.
Because the reason we only get a 24-hour warning in this scenario is because we literally couldn't see it coming.
We'd be totally blind to it.
Right. I mean, imagine you're a sailor on a pitch-black ocean on a moonless night, and there is a completely unlit matte black stealth ship sailing right at you.
That's a great way to picture it.
It's making no noise. It has no lights. The only possible way you can tell it's there is if you stare really hard and happen to notice the water physically bending around the hull of the ship.
Yeah, the way water bends around a hull is a perfect parallel for what we call gravitational lensing.
Because they don't emit light.
Right. Black holes emit absolutely zero detectable light or radiation themselves. They are pure absence in the dark.
So how do we ever see them?
Well, the only way our telescopes can spot a dormant, isolated black hole is if we happen to catch it passing directly in front of a background star.
Oh, I see.
The extreme gravity of the black hole actually warps and bends the starlight around its edges. It looks almost like you're viewing the distant star through the curved base of a wine glass.
But space is infinitely huge. I mean, we're not looking everywhere all at once.
Exactly. If we aren't pointing our instruments at that exact patch of sky, looking for that exact visual distortion, a stellar black hole could slip right past our early warning systems.
So we'd have no idea until it was practically on top of us.
We would just be incredibly lucky to even have 24 hours to process what was happening, or, unlucky, depending on how you look at it.
That is wild. So the clock starts, the silent alarm goes off. Because we can't see the black hole with our naked eye, the first signs of doom aren't visual at all.
No, not at all.
They are physical. The very first place on Earth to scream that something is wrong wouldn't be the sky. It would be the oceans.
Because gravity travels at the speed of light. So long before the black hole gets close enough to swallow us, its gravitational influence washes over the solar system.
There's this invisible wave.
Right, and gravity's first target is equilibrium.
And our scientific instruments would catch it first, right? Like the DART mission out in space or the LEGO observatories here on Earth.
Yeah, LEGO in Louisiana and Washington State. They would detect actual ripples in space-time moving toward us.
Ripples in reality.
Basically, yeah. LEGO is specifically designed to detect the microscopic stretching and squeezing of reality itself caused by massive gravitational events.
But usually from way further away.
Right. Under normal circumstances, it listens for black holes colliding millions of light years away. If a 10 solar mass object entered our immediate neighborhood, those sensitive laser interferometers would just go completely haywire.
But before the scientists could even call a press conference to explain the data,
Yeah.
the animals would know.
Oh, for sure.
I mean, migrating birds, deep-sea creatures, elephants, they are highly sensitive to electromagnetic and gravitational changes. They would sense the disruption and start acting completely erratically.
Caught a panic?
And then the oceans rise up.
Because the tides are the most visible, everyday manifestation of gravity we experience on Earth.
Right.
Right now, our tides are controlled in a delicate dance primarily by our moon, which has a tiny fraction of Earth's mass.
Barely a blip compared to a black hole.
Exactly. Now, introduce an intruder with 10 times the mass of our sun. The gravitational disruption throws that delicate dance into utter chaos.
If you're listening right now and you live in a coastal city, your first instinct might be to think, well, wait, if the water is rising, why can't we just brace for it?
Like a storm surge.
Right, like we have seawalls, we survive hurricanes. During Hurricane Sandy back in 2012, water flooded 51 subway stations in New York, but the city eventually recovered. Couldn't we just sandbag, get to high ground, and wait it out?
What's fascinating here is that you have to unlearn how you think about water movement entirely.
How so?
Well, when you think of a hurricane like Sandy, you are thinking of weather. You are thinking of severe wind pushing water ashore, or barometric pressure allowing the sea level to rise slightly.
Right, surface level stuff.
This scenario is completely different. This is gravity itself physically lifting the ocean towards space.
So the water isn't being blown, it's being pulled.
It's a tidal bulge of apocalyptic proportions. You cannot build a seawall against a force that is actively trying to pull the ocean off the surface of the planet.
That is terrifying.
Right. A place like New York, with the Hudson River and its harbor, simply becomes a funnel for the entire Atlantic.
Just a wall of water.
Yeah. And Miami, which is built on highly porous limestone just meters above sea level, wouldn't just flood from the coast. The water would push up from underneath the ground itself.
Oh, wow. So nowhere is safe.
No. Mumbai, a densely packed peninsula with 20 million people, goes entirely underwater. And the crazy part is, this is just the opening act. The rising tides are merely a symptom of the real disease.
Right, because the destruction moves from the oceans into the sky. Since this new gravitational pull is fundamentally altering Earth's place in the solar system, our orbit starts to shift.
Yeah, we start moving.
Just millimeters at first, then meters, then kilometers. We are actively being pulled out of the habitable zone. And I want to make sure we understand exactly how that happens. We are essentially traveling at roughly 67,000 miles per hour around the sun right now.
Correct.
How does the black hole derail that much momentum?
It's a massive gravitational tug of war. Earth stays in its orbit because its forward momentum is perfectly balanced by the sun's inward gravitational pull.
Like swinging a ball on a string.
Exactly.
Yeah.
But when the black hole gets close enough, its gravity begins to compete with the sun. It starts hijacking Earth's momentum.
Depending on the angle it comes in from.
Right. Depending on the approach, it either speeds us up and slingshots us outward or slows us down and drags us inward. Either way, that delicate balance is shattered.
Here's where it gets really interesting. There is this incredible analogy from the source material, to describe just how fragile our atmosphere is during this whole tug of war.
Oh, the basketball analogy.
Yeah. If you were to shrink Earth down to the size of a standard basketball, the atmosphere, the air we breathe, the clouds, our entire weather system would be thinner than a single layer of plastic wrap tightly sealed around that basketball.
It is a really sobering visualization.
It changes how you look at the sky.
It does. We look up at a blue sky and think it goes on forever, like an endless ocean of air above us. But in reality, it's just a razor-thin film clinging to a rock.
And as our orbit shifts, that plastic wrap starts to tear. The jet streams, those massive rivers of air flowing 10 kilometers above our heads that dictate global weather, they completely destabilize.
Because the jet streams are driven by the temperature difference between the equator and the poles, combined with the rotation of the Earth.
Right.
When you yank the Earth out of its designated orbit, the temperature gradients go insane. The rotation is affected by the immense tidal drag of the black hole. The entire engine of our climate just shatters.
And the result is immediate chaos. I mean, Chicago experiences apocalyptic winds. The Great Plains face superstorms that defy recorded history. We're talking temperature swings of 30 to 40 degrees in a matter of hours.
Just absolute extreme weather everywhere.
But the scariest part to me isn't the wind. It's the invisible shield dropping, the magnetosphere.
Ah, yes. The magnetic field.
I always pictured the magnetic field as something generated by, like, static north and south poles, like a bar magnet. But it's actually molten iron actively spinning inside the core, isn't it?
You've hit on the exact mechanism there. It's generated by the dynamo effect.
The dynamo effect.
Right. Deep underground, liquid iron and nickel in Earth's outer core are constantly churning and swirling as the planet rotates. That movement of conductive fluid is what generates our protective magnetic shield.
And that shield is super important.
Crucial. It's what keeps the solar wind from stripping away our atmosphere, and it blocks lethal solar radiation.
So when this 10 solar mass black hole starts pulling on the Earth, it isn't just lifting the oceans, it's physically pulling on the liquid iron core itself.
It violently distorts the internal churning of the planet. The gravity pulls on the heavy metals in the core, altering the rotation and disrupting those convection currents.
So the engine breaks.
Basically, the dynamo effect stutters, it warps, and finally the magnetic shield fails entirely.
Leaving us totally exposed. The surface of the Earth is suddenly bombarded by solar radiation.
Yeah.
It wouldn't, instantly fry us, but it would violently accelerate the atmospheric collapse.
It's an incredible domino effect.
It really is. Starting from a tug-of-war in space, affecting the deep molten core, killing the magnetic field, shredding the high-altitude jet streams, right down to the superstorms on the surface.
And that shifting orbit inevitably drags Earth to the point of no return. We transition from atmospheric chaos to planetary dismantling.
The end of the line.
Yeah, we enter the 40,000-kilometer kill zone. Astronomers call it the Roche limit.
Right, the Roche limit. I've heard that term thrown around in sci-fi, but I always pictured it as some kind of invisible force field or a cosmic tripwire that you cross and suddenly explode.
A lot of people do.
So what is actually happening physically to the planet when we hit that?
Well, the Roche limit is a mathematical boundary, not a physical barrier.
Okay.
It is the exact distance at which the tidal forces of a massive object, in this case our black hole, become stronger than the gravitational forces holding a smaller object, like Earth, together.
So the planet can't hold itself together anymore.
Essentially, yes.
Yeah.
It's the point where the glue of Earth's own internal gravity fails.
And when you look at the math for an object this massive, the distance it requires to break a planet is terrifying.
It is.
For a 10 solar mass black hole, the Roche limit for Earth is about 40,000 kilometers. To put that in perspective, our moon is 384,000 kilometers away.
So the black hole has to get incredibly close.
Cosmically speaking, yeah, practically next door before the planet physically breaks.
But once it crosses that invisible mathematical line, the mechanics are incredibly brutal.
When you hear about a planet being eaten by a black hole, the visual that usually comes to mind is a giant cosmic vacuum cleaner.
Right, the vacuum analogy.
Yeah, just a dark vortex that swallows the entire planet whole like a marble. Is that remotely accurate?
The vacuum cleaner analogy is actually a huge misconception.
Oh, really?
Yeah, a black hole doesn't suck matter in like a vacuum, it pulls it via gravity. To understand the destruction of Earth, you have to understand differential gravity.
Differential gravity, what's that?
Well, gravity gets stronger the closer you are to the object.
Okay, so distance is the key factor.
Exactly. When Earth crosses the Roche limit, The side of our planet facing the black hole is significantly closer to the singularity than the side facing away.
Oh, I see.
Therefore, the front side is being pulled significantly harder and faster than the back side.
So the front is basically falling faster than the back.
The result is sheer, overwhelming stretching force. It's not a pop, it's a pull.
Just ripping it apart.
The crust of the Earth, which feels so permanent and rock solid beneath our feet, simply cannot withstand that tension. Mountains crumble. The tectonic plates are ripped apart from each other. The planet is literally stretched out like a teardrop.
The technical term for this process sounds almost too silly for how horrifying it is.
You mean spaghettification?
Yes.
Spaghettification.
It sounds like a joke, but it's very real. Spaghettification is the literal process of a three-dimensional object being stretched into a long, thin ribbon of matter.
Just unspooled. The solid rock of Earth would peel away, layer by layer. It turns into a stream of crushed rock, exposed magma, and superheated gas, continuously spiraling down toward the singularity.
It's gone.
Within hours of crossing that line, Earth ceases to be a planet and just becomes part of a glowing accretion disk.
I mean, it's almost impossible to visualize the ground beneath you just peeling away into space.
It is hard to wrap your head around.
And yet, this is where the narrative takes a really fascinating pivot, because with physical destruction absolutely guaranteed, we have to look at how humanity reacts.
Right, what do we do?
Yeah, what do we do in those final 24 hours when the math proves we have zero chance of survival?
The answer we see time and time again in these models is remarkably profound.
It really is. Every space agency on Earth mobilizes, not to build an ark, not to escape. You simply can't outrun a black hole in 24 hours.
Not a chance.
They mobilize to document. NASA's Deep Space Network, which is this massive web of giant radio antennas spread across California, Spain, and Australia, turns all its power outward.
Pointing away from the danger.
Right. They start broadcasting everything they have. Math, languages, human faces, music, just throwing it into the void.
And the James Webb Space Telescope, parked 1.5 million kilometers away from Earth, would lock its sensors onto the black hole.
Just watching it happen.
It would continuously transmit telemetry and structural data right up until the exact moment its own systems fail.
There are even models suggesting SpaceX Starships theoretically launching. I mean, they wouldn't get far enough or fast enough to survive, but they would launch anyway.
A desperate, defiant attempt to clear the atmosphere.
Exactly. And then there is the Svalbard Global Seed Vault.
Ah, the Doomsday Vault.
Yes. We're talking about a facility buried more than 130 meters deep inside a mountain on a really remote Norwegian island.
It's built to last.
It's surrounded by permafrost, shielded by thick concrete, and designed to survive nuclear war or asteroid strikes. It stores over 1.3 million seed samples of nearly every plant on Earth.
And what did they do?
In those final hours, someone goes down into the ice, and they seal the final vault door tight.
They seal a vault that is mathematically destined to be spaghettified into a ribbon of gas.
So what does this all mean? Why would humans bother throwing seeds into a bunker or beaming math into empty space when the very atoms of the planet are about to be shredded?
If we connect this to the bigger picture, it reveals the absolute core of human psychology.
Yeah.
It is the deep-seated message-in-a-bottle instinct.
Yeah.
We're a species defined by our need to leave a legacy.
We want to be remembered.
Even in the face of total, unavoidable annihilation, our primary instinct isn't just to despair or hide. It is to say, we were here, we existed, we learned things, we grew food, we made music.
It's a refusal to go quietly.
The sheer stubbornness of firing a rocket at a black hole you can't escape is arguably the most profoundly human response possible. It is a rebellion against the silence of the universe.
It is beautifully stubborn. And, contrast that with the silence of the universe, and it brings us to a very chilling reality check.
Back to the real world.
Right. Obviously, there isn't a black hole 0.1 light years away right now.
Thankfully.
But we aren't completely alone out here.
No, it puts our existence into stark relief when you look at our actual cosmic neighborhood.
Take Gaia BH1, for example. It was discovered by the European Space Agency back in 2022. It is the nearest known black hole to Earth.
The closest one on record.
And it is sitting right now just 1,560 light years away. In cosmic terms, that is literally just down the street.
Right next door.
And it's just sitting there, dormant.
And that is only the closest one we have managed to find. The Milky Way galaxy is vast, and we have only successfully mapped a fraction of it.
A tiny fraction.
Because stellar black holes don't glow, and because they don't announce themselves with massive accretion disks unless they are actively feeding, statisticians and astrophysicists estimate there could be up to 100 million unconfirmed stellar black holes drifting through the dark spots of our galaxy.
100 million invisible wrecking balls.
Floating out there. And we only find them by the shadows they cast or the light they bend.
You know, the philosophical conclusion to draw from all this physics is incredibly grounding.
It really is.
The universe isn't hostile. It isn't actively hunting us with these stellar remnants. It is simply totally indifferent.
It doesn't care either way.
Right. When you consider the fact that Earth survived the late heavy bombardment, it survived the asteroid that wiped out the dinosaurs, it survived countless extinction-level events.
It's a miracle we're here.
Our everyday, boring existence, that morning coffee in the kitchen, is just cosmically improbable.
This raises an important question, one that really lingers long after you finish looking at the terrifying mechanics of differential gravity.
What's that?
In this scenario, humanity spends its final 24 hours doing what we've always done, observing. We name the black hole, we measure its mass, we calculate the Roche limit, we broadcast the raw data of our own destruction into the void.
We document it all.
Right. If the universe is entirely indifferent to our survival, if it can wipe us out without a second thought, is our ultimate cosmic purpose simply to be the universe's way of observing and documenting itself before the lights inevitably go out?
Wow. That is exactly the kind of thought that fundamentally changes how you look at a starry sky.
It really does.
Well, we want to thank you for joining us on this deep dive. The physics of our universe are terrifying.
Yeah.
But the fact that we can understand them, that we can measure the dark and predict the math, is something to be incredibly proud of.
Absolutely.
So the next time you're having that completely normal morning, your coffee is brewing, and you're casually scrolling through your phone, take a second to appreciate the quiet. It is a very rare gift in a very loud universe.